is that Zijo is the indicator that the new frame I has the representative old frame J. Clear? So in general, it is something like this, that Zij is basically saying that your J is representative of I. Okay, so this is what it means. Okay, so it means that so if it is O, then it means that jth old frame is representative of ith new frame. Okay, and if it is Zijn, then it basically denotes that jth new frame is a representative of ith new frame. Now, and then we are trying to minimize the total dissimilarity. Okay, so what does this mean? So I will come to the second term in a minute. Okay, so I will come to the second term in a minute. But these first two terms in the objective function, what does this mean? So this means that you select the dissimilarities for select the representatives for all the ith new frame among among either the old frames or the new frames. Okay, and you select the ones which have minimum dissimilarity with I. Okay, that is what this part of objective is doing. So it is asking you to select, it is basically allowing you to select the representative for all the new frames which are denoted by the index j. Okay, in such that the total dissimilarity between the representatives and their original frames is minimized. Okay, now what is this part doing? The second part of the objective function, the second part of the objective function is saying that it is taking all the representatives which are there in the new frames. You see, only the Zijns are taken. Okay, and it is taking the norm of them. So this is basically, in some sense, that how many representatives have you chosen from the new set. So what will happen at the end of it is only the representatives of the new set will be taken. All the other frames will be dropped. Okay, so from the new set, in the existing set you have already the compressed set, which is RT. Okay, if a new frame has a representative in the old set, then nothing needs to be taken. But if a new frame has a representative in the new set, then only the representative will be taken, the new frame will be dropped. And the second term is a measure of how many representatives are there from the new set. Okay, so you are also minimizing the number of representatives which are there in the new sets. So there is a weighted objective, lambda is the weighting factor. So if lambda you set to, it is a factor that the user gives as input. So if you set lambda to 0, then there is no penalty for selecting a large representative from the current set. But if lambda is very high, then you have a lot of penalty for selecting representatives from the new set. And now what is the third equation or constraint doing here? It is just saying that every new example will have exactly one representative. So Zijo and Zij n, when you sum over all the j's, that is all the possible representatives, they should sum to 1. So only one of them should be selected. Okay. So this is what this formulation is doing. Okay. So I hope the formulation is clear. Okay. And now I can give you some results. So basically, so we have some baseline methods. One is so by the way, here there is so your objective, remember, is that when you train using the selected set, okay, the model, then you should be able to your total your test error, okay, should be minimized. Okay, your test set error should be minimized. So so these are some of the baselines. Okay, so one of the baselines is the one that just involves distinctiveness and uncertainty. Others are random, and another baseline is cumulative, where there is no data reduction. Okay, and we compare this with the following method: shift only, shift plus loss, okay, shift plus distinctiveness plus uncertainty, and the whole set 6. So this SDU and shift are both active learning methods, and SL and SDUL are basically dependent on the label. And we can see that for 100:4 compression ratio, okay, there is a drop of, so cumulative is your baseline, and you are getting this accuracy and mean IOU, okay, and your accuracy is something like here. So here it is 85%, 86% maybe, and it has come down to more like closer to 85% here. Okay, so if we are using SDUL, whereas if you are using, let's say, only shift, then the drop is about 1.6%. Okay, and it comes down to almost 84% here. Okay. And the others are like this. Okay. Similarly, you can see the number in the bracket. So if you are using 100:9, so you select 9 out of every 100 frames, you get a drop of about 0.6. And if you select 15 out of every 100 frames, you get about 0.5. So maybe, this 11x reduction, this 9 out of every 100, is kind of a good reduction. Okay. Okay. So now, so any question on this part? Okay. So now I am just going to describe the autonomous driving model. Okay. So so there are various types of autonomous driving models. Okay. So some of the older ones. So I'm just going to go quickly over the literature review. Okay, because this is not very recent, and also not very I will say not very interesting. So broadly, there were the modular pipeline approaches, where people used to design like a semantic segmentation model for the, so there used to be this perception stack. Okay, so there used to be many different algorithms.
One question is there, sir.
Yeah, please. Yeah.
Has there any role in row value in formulation problem?
In the row value, yes. Okay, so thank you that you asked. Okay, so here the row is basically selecting the weightage you give to shift. Okay, so if row is 1, then it is shift only. So the way we select these methods is by varying these rows and etas. Okay, so if row is 1, then it is just the shift model. Okay, if we want to, so eta 1 plus eta 2 plus eta 3 should be equal to 1. Okay, so if we want, let's say, only shift and then distinctiveness and uncertainty. Okay, so I will set eta 1 to 0, and let's say I am giving equal weightage to distinctiveness and uncertainty. Then I will set eta 2 to 0.5 and eta 3 to 0.5. So that is how we select it. Is it clear?
There is another question from the same participant. Can you look for a row optimal value?
Yes, yes. So very good. So can we look for a row optimal value? Yes, indeed we can, and we are working towards that. There's a problem there. So the problem is that row optimal for what, right? So what you really want, uh, so you cannot take the training set loss, because I mean, I don't know if you can, if it can be interactive. So can anybody think why you cannot take row optimal or eta optimal using the training set loss? Okay, so I don't know if they can talk. So I will just give the answer. The answer is, you see, the loss is already here. Okay, so the optimal for training set loss will be what? Rho is equal to 0, eta 1 equal to 1.
One answer given with some objective measure in constraint scenario.
With some objective measure in constraint scenario.
Yes.
Constraint scenario. Okay, I am not sure I understand the answer. Okay, let me describe the answer. So here the simple idea is that you already have loss as the signal. Okay, so basically, if you try to minimize the training set loss, okay, then what will happen? It will select rho to be 0, eta 1 to be 1, and all the other etas to be 0. So that is the optimal. So we know the optimal solution, because if you want to, if you want to minimize the training set loss, okay, then from the new set you select the examples which have minimal loss, okay, and include them in the training set. Okay, so then what will happen is that you will have a training set which is more compliant with each other. Okay, but that is not what you want. Okay, so you have to, you can select, so it is a good ask to select row which is optimal, but optimal with terms of what? So the next thing comes that maybe it should be optimal with respect to validation loss. Okay. Now, if that is the case, then it is possible to solve for that, but the resulting problem is no longer a convex optimization problem. Okay. So another thing I forgot to mention here, probably I should mention it here, is that this formulation, okay, so this whole formulation, an attractive approach is that this is a convex optimization problem. So we are also trying some non-convex formulations, but there you have much more choices. But there the problem is that you are never guaranteed optimal solution. That is one problem. The other problem is that, see, people have been studied convex optimization for a long time, and there are very, very good generic convex optimization solvers. So we have used, for example, CVX, okay, and it is very fast, okay, because people have developed, in the optimization literature, people have developed many very fast algorithms for solving convex optimization problems, okay. But if we have to develop the algorithm ourselves, then it is not so sure. So that is another thing. Okay, so I hope that clarifies the doubt. Okay, but that is a very good question. Okay, so and we are kind of trying to do something on those lines also. So, okay, so now we come to this modular. So these are the existing approaches for autonomous driving. So one is modular pipeline. So mainly this is something like, so I have given the references here. So this is a very complex pipeline. Okay, this is a very complex algorithm that people have set up. Okay. So then with the advent of so complex algorithm, as you can understand, it has its own problems. If any of the components fail, then debugging is a problem. All those things, the debugging and maintenance of the whole system, then incorporation of new data, all those things are much more expensive. Okay, so what did deep learning do? Deep learning said, you don't have to build all these complex modular pipeline approaches. You can just do end-to-end learning. So end-to-end learning means that you don't have to do all these separate semantic segmentation algorithms, separate object detection algorithms, separate pedestrian detection algorithms, separate traffic light detection. You just, all this information is there in the input image. So you just take the input image and you directly output the controller actions. So controller actions are basically brake, throttle, and steer. Okay, so you directly do that. And again, this approach was sort of tried out by a couple of folks at NVIDIA. So NVIDIA people, they had this GPUs. And one of the major applications they were saying is autonomous driving, because GPUs are highly parallel and they could do this autonomous driving processing in a parallel manner very fast. Okay, so so they did it, but it was successful to an extent, but not greatly, and the reason is that there is not much control. Okay, so you have a huge neural network. Okay, it takes a lot of time to train. Okay, it takes in a lot of data, and you use a very powerful computer to train it, and a very powerful computer to execute it also. Okay, so for executing the controller on the car, you may use a GPU. But for training also you will need to use GPUs, but many of them, okay, because you need to process, a much larger volume of data, okay. And so anyway, so it turns out that it is hard to train such end-to-end learning models, and it is even harder to debug such models. So suppose you train, and then on a particular frame there is an error. Okay, you don't know why the error is there, so there is very little explainability. Okay, so okay, so this is also end-to-end learning. Okay, yeah, so end-to-end learning people have done a lot. Okay. So so here I want to mention something. Okay. Yeah. Yeah. So then came. So actually, I'm calling this end-to-end learning because this is an end-to-end learning framework. But uh, this class of methods is kind of called affordance learning. Okay. So this is the kind of approach that we take. So what is affordance learning? So affordance learning says that you don't directly learn the controller action. Okay. Instead, you learn some high level commands from the image. So for example, this is more closer to what humans do. So high level commands can be, let's say, you may say that turn right, okay, or go straight, or stop, okay, things like this, okay, and from that, so once you have the high level commands, the next stage is actually very simple and predictable. So people have what are called these controllers. Okay, so in the control theory literature, people have developed controllers which takes these high level commands, and they can generate the control signals. Okay, and these controllers can be learned, or they can also be some sort of static controllers. Like there are signal processing based controllers, nonlinear signal processing based controllers, like the PID controllers, feedback controllers, all these kind of controllers. The advantage of these controllers is that their stability behaviors is known. Okay, so if you can, let's say, you generate a command like go straight, okay, you know that the controller will stabilize itself, okay, because that analysis has been done, okay. But the neural network model, it may give it may keep getting faster and faster and faster speed, okay, and it may not be able to, it may go too fast or something like that, okay. So all these things are not predictable, but in case of a controller, these things are predictable. Okay, so this is kind of the most accepted paradigm now, that instead of predicting the actual controller commands, you predict some high level affordances. Okay, and there have been many of these. So there have been so the next part is something called conditional imitation learning, where what you do is not only do you learn the affordances, okay, or rather I should say this conditional imitation learning is the other side of it, where it predicts the driving action, okay, but it predicts it via a conditional network. So what is a conditional network? Conditional network is where you also give an input driving signal. So you may say, for example, from the planar module, so at a particular intersection, you may want to go left, okay, or you may have a planar module which says that the car in front of you is not moving for a long time, okay, you want to actually take your own car into another lane, okay, left lane or something, and then you want to go. So the planar module will generate the waypoints accordingly, and these waypoints will be input to your affordance learning module, okay, or yeah, so yeah, so let me come to the conditional affordance learning directly. Okay, so what does conditional affordance learning do? Okay, so you have your agent. Okay, uh, now you have this perception module plus this directional commands, like I said, and these directional commands could be coming from a route planning module. Okay, so like I said, a planning module could be giving you the waypoints as to where you want to go. Okay, and your perception module is just the neural network that we talked about. So it takes the camera image as the input, okay, and this whole thing is fed into a neural network model, okay, which predicts the affordances, okay, and from the affordances there is a control module, okay, which will directly predict steer, throttle, and brake, and then you can test using the simulator. Okay, so this is kind of the architecture in which we work. Okay, so so our job is basically to train this neural network model. Something we don't work on. So this comes with the Carla. So the Carla simulator also gives you a route planning module. So if you have a pair of endpoints, origin and destination pair, okay, Carla will generate the the route planning module will generate the intermediate waypoints. But like I mentioned, your intermediate waypoints can also be generated by some other module, like in case of robot navigation and all these things. You may have seen that these intermediate waypoints are generated. There are actually planning algorithms which explore the environment and also generate the waypoints accordingly. Okay, so there are so that is another problem which we will not discuss here. Now, what are the affordances that we learn? Okay, so the affordances that we learn are so there is the hazard stop. So hazard stop, it takes two values, true or false. Okay, so the hazard stop is true when there is a person in front of you. Okay, otherwise it is false. Okay, or even if there is a car, it will still be true. So either there is a person or there is another car. Okay, it will be true. Okay, then there is the red light. So you have to predict whether whether there is a red light or not, and basically whether the red light is true or false. So if there is a red light and the signal is red, then it is true. Otherwise, it is false. So it has to detect whether there is a red light, and if there is a red light, it should detect whether it is actually red or it is green. Okay, if it is green, then also it should predict false. Okay, then there is the speed sign, which is which is basically it says whether there is a speed sign or not, and if there is a speed sign, then what is it? Is it 30 kilometers per hour, 60 kilometers per hour, or 90 kilometers per hour? Okay, so what is the speed limit? Okay, and then there are three more continuous affordances. So one is distance to vehicle. So it is basically the distance to the vehicle in front of you. Okay, and if the vehicle is very far away, you just predict 50. Otherwise, you predict the actual distance. Okay, and yeah, if you are very close, then you predict 0. Then there are the two steering related affordances. One is called the relative angle to the center line. Okay, so like I mentioned, so it is expected that the road will have a center line. Okay, and now this particular affordance will predict what should be, rather what is your relative angle to the center line. Okay, and the last one is distance to the center line. So how far is your vehicle from the center line? Okay. So these are the affordances, and here in the interest of time I will not go into the detail of how you can get this from the simulator, but there is a bunch of calculations that you can do in order to get all these affordances from the simulator. So I will skip this slide. Okay. Now comes our conditional affordance learning model stack. Okay. So by the way, this conditional affordance learning model was developed by a group in EPFL Europe. Okay, so the original conditional learning model was developed by a group in Europe. I think I have given the reference in the slide. Okay, so what does the conditional affordance learning model do? So, so it has basically, like I mentioned, if you see the affordances here, there are these affordances. So this relative angle and center line distance, these are conditional affordances. Okay, so you see the conditional column here is yes. Okay, why are these conditional affordances? These are conditional affordances because if your next waypoint is trying to take you to the left or to the right, then that information should be available to you at the time of prediction of the relative angle. Otherwise, you will not be able to predict the relative angle. Okay, so you will be able to predict the relative angle conditioned on the next waypoint direction. Okay, so this is what is here. So there are these conditional blocks to which the directional commands go. Okay, and there is a feature extractor. So the feature extractor is a so they use this VGG network. I'm not sure. So you know about the VGG network, but you can use any feature, any generic feature extractor network from the computer vision, and then you can train it further. So so they use the VGG network. Okay, so there is the feature extractor network. Then there is the memory network. So the memory network takes in the last, like in here it is given capital N many frames as input. Okay, so it takes the last N many frames as input, and then it passes them through some kind of a recurrent neural network, and then feeds them to these task blocks. Okay, so there are 6 tasks. So it is a multitask learning problem. So there are 6 tasks, one corresponding to each affordance. Okay, and these 6 tasks are sort of yeah. So these are the tasks that are predicted, and then there are these affordances are yeah. So basically they go into the controller for the longitudinal and the lateral control. Okay, and these task blocks are basically feed forward layers. Okay, so we have played around with it, but typically these are like 2-layer feed forward networks, and with some thousands of nodes in the hidden layer. Okay, and yeah. Okay, and now how does the controller predict the affordance? So there is the longitudinal controller. Okay, so so basically it takes yeah, so it takes basically this affordances, and it has this logic that if hazard stop is true, then you brake. Okay, if red light is true, then you brake. Okay, if the current speed is greater than speed limit minus 15, then you predict this over limit, and accordingly there is a feedback controller which basically applies the brake, okay, and yeah. So and if your vehicle distance is less than 35, then it goes into this following mode, okay, and there basically it again applies the brake, okay. Otherwise it is just in cruising mode, so it keeps applying throttle to maintain the current speed. So it is something like this, okay. uh, okay, and this lateral controller is again a PID controller, okay. So it takes the center line distance and the relative angle, okay, and it generates the steer angle which is required to achieve the center line distance and the relative angle, okay. So yeah, okay, so okay, so now some results. So we collected about 30,000 frames, and then out of that we collected these keyframes, and there are about 6,000 of them. Okay, and basically our test set is 7,000 frames. Okay, and so our job is basically to measure the performance of our prediction model on all these tasks. Okay, so these are the accuracies that we give. Okay, and these are the yeah, so these are the accuracies on the selected subset. Okay, so subset selection is performed using the technique that we mentioned earlier. Okay, okay, and yeah, so this is kind of so there are two things that I want to mention here. This is kind of an ongoing work, so it is under submission. So we have done a lot more things here. So I am not mentioning any more results, but there are two main problems. One is when we reduce the when we reduce the what do I call the set of frames. Okay, you remember this, let me show you this. So remember there is a memory. Okay, so your prediction now depends on not only the current frame but also the previous frames. Okay, and if you don't reduce the data set, then your frames are at constant interval, at constant sampling rate. Okay, and then if you so then you can do like a much so you have more consistent information for prediction of the affordances. Okay, but if you reduce some of the frames and then if you drop some of them, that may no longer be true. Okay, so that is number one problem, and for that what we have done is we have designed something called cal with timestamps. So it works slightly better, but we are not too happy with it, and it is not yet published. So we have put the results here. So it works slightly better, but not too much better. And it is basically just that you give a timestamp weighted feature as input in addition to the actual features. Okay, so this is one problem that we are facing. The other problem is that it is a multitask approach actually. So you have many tasks and you have loss corresponding to each of these tasks. Okay, so how to give importance to each of these? So that is the second problem for selecting, which is not there in case of selection for semantic segmentation. Okay, so that is all I had. I don't know why this is. Okay. So, but okay. So I will just stop here. I think we are out of time, right? So this was the next set of things that I wanted to discuss. But I think we will stop here. And if there are any questions, so I would really like to have a discussion and questions.
Thank you, sir, for the wonderful lecture. And we will see that if any questions are there on chat box. If anybody is having any question, please you can put your question in chat box, or you can put your audio on and you can just ask question.
Okay, Shanti Maiti is asking, can route planning be linked as a routing algorithm like wireless network? Yes. So I think in the there is a field in this robotics called planning and navigation. Okay. So I'm not an expert on that, but so we have done one work. So it is. I think there is a. It is. I'm not sure it is a routing problem. Maybe it is a routing problem. Uh, so there basically what you do is you have to generate an exploration mechanism. Okay, so so it also depends on route planning where actually. So if it is, so there are two levels of route planning, right? So one is that you have the road network and then you want to go from one point to the other. So which roads do you want to take? So that is one level. But also inside the road, there may be some obstacle in front of you. Okay, so you may have to take the other lane. Okay, or take go to a little bit to the right or a little bit to the left. Okay, so that is part of this exploration approach, and you can check out. So there is this called RR trees algorithm, which are basically robot motion planning algorithms, which can also be used there. But I think just for if you are thinking of it as something like what Google Map generates, like you give a origin and a destination and it will tell you a route through a robot network, maybe that can be solved as a routing problem. Maybe so. So thank you, Hirak is saying. So Shanti Maitri, maybe in the framework for MDP in RL for obstacle handling. Yes, I think yeah. So yeah, so so there are some works in the RL community for obstacle handling also using Markov decision process. Uh, yes, I am not 100% aware of that, but I have, yeah, I have seen those works also. Okay, so any other questions?
So I think no more questions are coming. We'll just wait for 1 minute if more questions are coming. Otherwise, we will
Okay.
just end. So just
Okay. Okay, thank you very much, everyone, for giving your attention.
thank you, sir, for your wonderful informations which you gave. So if anybody is want to work on this, they will get some idea for the starting of their work. And if any queries they have, they can mail you also. Thank you, sir,
Okay,
for
thank
the
you.
session. Thank you, sir. And we will just wait for the participants. We will just wait for the next session. The next session will be the lab session. So we'll just wait for some time. Thank you, sir.
Thank you very much. So I will go. See you all again at some point in time.
Thank you, sir.
Bye, everyone.
Thank you, sir.
Bye, sir. Thank you so much, sir.
Thank you, sir.
Hello.
Hello, madam.
Yes, yes.
Madam, we have received a few questions. Are they for preparation of test?
Yes,
Not
yes, yes.
Yes, you just,
Prepare for the
yes,
preparation.
for the test, it will help you.
Okay, ma'am.
This may help. This may help. Not that it
Yeah.
will come. All the questions will come, but this will
Okay.
help you. Okay.
Okay, sir. Thank you. Okay, ma'am. Thank you.
Ma'am, one question. Hello.
Yes.
When do we have